6.3 Day 1, Vectors in the Plane. We're going to represent vectors as directed line segments, write component forms of vectors, perform basic vector operations and represent operations graphically, and write vectors as the linear combinations of unit vectors. So there's a lot of basic things that we need to go over before we start our operations with vectors. So we need to know that quantities such as force and velocity involve both magnitude, which is just length. Magnitude is length, and we find the length by using the distance formula, and direction, and cannot be completely characterized by a single real number. So to represent such a quantity, you can use a directed line segment as shown in figure 610. The directed line segment PQ has initial point P and terminal point Q. So initial point P, terminal point Q. Its magnitude or length is denoted by P, and it's this line with the little, like half an arrow, and can be found using the distance formula. Two directed line segments that have the same magnitude and direction are equivalent. So for example, all of these here in figure 611, they are all equivalent. They have the same magnitude or length, magnitude is length, and then they're all going the same direction. So the set of all directed line segments that are equivalent to the directed line segment PQ is a vector in the plane written V equals P with that little half arrow on it, PQ. Vectors are denoted by lowercase, bold-faced letters such as U, V, and W. And then it says directed line segment. It also has this little line over it. Okay, so when we write it, we need to make sure we use the right notation. So example 1, we're going to show that two vectors are equivalent. Show that U and V in figure 6.12 are equivalent. So what we need to do is we're going to use the distance formula to figure out if they have the same magnitude, and the magnitude is just the length. So we're going to use distance. And that formula is, if you remember, D equals the square root of x2 minus x1 squared plus y2 minus y1 squared. So this is x1, y1, x2, y2. So the magnitude, we write that with these lines, two lines, and then that small little arrow here to show magnitude of this vector PQ. And then we plug it in. So x2 is 3 minus x1 is 0 squared plus y2, which is 2 minus 0 squared. And so that is going to be the square root of 9 plus 4, which is the square root of 13. Now let's do R. So the magnitude of RS, vector RS, is going to be the square root of 4 minus 1 squared plus 4 minus 2 squared. And so that is 9 plus 4 again, which is the square root of 13. So the distance, the magnitude is the same. They are equal. So now we need to look at direction. The direction, and we're looking at direction, we're looking at slope. So we want to use the slope formula, and that's y2 minus y1 over x2 minus x1. So let's find the slope of segment PQ. That one's pretty fast. It's y over x, so that is 2 minus 0, which is 2, 3 minus 0, which is, 3 minus 0, which is 3. And then, so that's the slope of PQ. And then let's look at the slope of RS. So we're looking at slope. And so that is going to be 4 minus 2 over 4 minus 1. So that's 2 over 3. So the slopes are the same, which means the direction is the same. So try this example here. Show that U and V in the figure below are equivalent. And then in the homework, you have to tell whether they are equivalent or not. So yes, these are equivalent. The magnitude for both is root 10, and the slope for both is 1/3. Let's look at the component form of a vector. The directed line segment whose initial point is the origin is often the most convenient representative of a set of equivalent directed line segments. We want it to be at the origin. So a vector is in standard position when the initial point is the origin. So we want it there. If both the initial point and the terminal point lie at the origin, then v is a zero vector and is denoted by 0 or 0, 0. Component form of a vector. So component form of a vector, we're going to see it in this form, okay, with those two on the outside. The component form of the vector, and the initial point is P, P1, P2, and the terminal point is Q, Q1, Q2, is given by this. So PQ, so the vector PQ equals Q1 minus P1, and then Q2 minus P2, which ends up being V1, V2, which is the V. The magnitude or length of V is given by, so, magnitude or length, so square root, it's the distance formula again, of Q1 minus P1 squared plus Q2 minus P2, or, and what we're going to use most often is this. So once we have it in component form, you just square both, add it together, and then square root, and that gives you the magnitude. So when magnitude is 1, then V is a unit vector. Moreover, when the magnitude equals 0, if and only if V is a 0 vector. Okay, just kind of little notes. So the two vectors U1, U2, and V1, V2 are equal only if U1 equals V1 and V2 equals, or U2 equals V2, just as an FYI. So let's find the component form and magnitude of the vector V that has initial point 4, -7, and terminal point -1, 5. So remember that the initial point is P, so that's 4, -7, which is our P1, P2. Then the terminal point is Q, which is -1, 5, and that's our Q1, Q2. And just remembering what we wrote above, to find the component form, you subtract basically the x's and subtract the y's, and then that would get you the component form of the vector. So let's do this. So we have V1, and that's going to be our Q1 minus our P1, and we have to do it in the right direction, meaning that the terminal point does matter. So let's do -1 minus 4, and that'll be our V1, so that is -5. Then V2 is going to be the Q2 minus the P2, and so that is going to be 5 minus a -7, or 5 plus 7, which is 12. So the component form of this vector is V equals -5, 12. Now the next thing we need to do is find the magnitude of the vector. And so remember, we could do the distance formula, but we already did a lot of the work already, so we're just going to square each one and then square root it. So to find the magnitude, it's going to be, so the magnitude of V is the square root of -5 squared, that, plus 12 squared. So this is the square root of 25 plus 144, or the square root of 169, or the magnitude of V is 13. So try this example on your own. Find the component form and magnitude of vector V that has the initial point -2, 3 and terminal point -7, 9. All right, if you tried this out, when you find the component form, you would find that you would get V1 is -5 and V2 is 6. So therefore, this is a component form of the vector V. And then the magnitude you would find is square root of 61.